Hi, I'm Jim Heffron. These are my lessons in calculus too. So we're talking about series. I mean, that's the central topic of this chapter. So I want to get to it. But before I do, just one last time. So some people watch these videos at 1, 2, 3, but there are sometimes people who will sort of Google and sort of land here, kind of parachute in. So just to speak to those, just for a second here, is that. This is the hardest chapter in the course. People have a lot of trouble with this chapter, and in particular, you want to be careful not to let this get away from you. So I have, before this video, I have a number of motivational videos that I think are a big help in giving a person some idea of what we're up to in this chapter, what we're accomplishing, and so you might want to look at those before you, before you get to here. Okay, very good. The second thing is, in part, because people have so much, struggle so much with this chapter. This is a long, relatively long video, just like the one on sequences, because these are the two foundational sections for the chapter, and so we're super keen that a person has the basics right. I mean, if you're confused about something at the end, one of the points at the end, okay, but you really want to get the sort of stuff at the beginning right. And so the thing today is that a series is defined to be the limit of the sequence of partial sums. So we spent a lot of time trying to nail that down. So you might want to, in the middle, pause, get a drink of water. I'll mention a point, but you might want to do that. It's kind of a long video. Okay, very good. Let's get to it. Okay, so series, the main section, the point of this chapter is infinite series, and so here we are introducing them. So our motivation is that we intend to make sense of things like the equation in the first line here that have an infinite sum. Okay. We've already seen these Taylor polynomials for f of x equals e to the x centered at a equals 0. I just plucked that function out of the air just to work with a function, and I evaluated them at x equals 2. See the x equals 2, and you see these numbers, and of course everybody who has taken calculus 1 and now calculus 2 is saying to themselves, well, these numbers are approaching a limit. So we'll take the limit of that sequence, here it is, the limit of that sequence, the limit as n goes to infinity of t sub n of 2 to be the definition of the result of plugging 2 into this infinite expression. So if you ask me what happens when you plug 2 in there, I'll say, well, it is the limit of the sequence of partial sums. What happens if you plug in 3? Well, it's the limit of the sequence of partial sums where you had instead of 2, where you had instead plugged in 3. 5, 10, minus 41. So similarly, if we plug 3 into the Taylor polynomial, then we get these numbers here. I won't bother you with the calculation, but I just got my computer system, which is Sage, to come up with the numbers to 3 decimal places. And then we'll take those numbers are approaching a limit, and we'll take that to be the definition of the result of plugging 3 into this infinitely long expression. Okay, so by the way, this is a 20.063, and the real value of e cubed is 20.086. So it's approaching that limit. So that comes out to be the correct number. And likewise, if you try x equals minus 1.5, so I wanted a negative and I wanted a number that had some decimal places to it. So you plug minus 1.5 in, then you get a bunch of numbers. Here are all the numbers, and you say to yourself, it looks like it's settling down at 0.223. We will take the limit of that sequence, the limit as n goes to infinity of the t_n's of 1.5. That's a discrete limit, so we had to talk about discrete limits in order to make sense of it. But anyway, we will take the limit of that sequence to be the definition of the result of plugging 1.5 into this infinite sum. Okay, and I'm just noting that the 223 is in fact, to 3 decimal places, the right answer. It is indeed e to the minus 1.5. Okay, so we're trying to make sense of infinite sums, and then later on we'll attach them to functions like e to the x. I mean, you can only do so many things at once. So we have to get used to sums. So it has been my experience. Sometimes people come into the class and this is not something they've done a lot with. So we'll often need the summation notation. So just ask folks to write out the first 4 terms in the summation. And as always when I do this, I think the right way for you to approach this is to pause the video, take out a piece of paper, give it a try, and when you come back and you can see the answer and you check whether you did it right. Okay, so I'll give you a second to pause the video. Okay, great. You plug in j equals 0, j equals 1, j equals 2, j equals 3, etc. Okay, I actually only asked for as high as j equals 3, but you could keep going higher, of course you could. Next one. Okay, and likewise you plug in j equals 0, I equals 0, I equals 1, I equals 2, I equals 3, and you notice that we're getting alternating signs, alternating SIGNS. The bottom of the fractions are squares, starting with the square of 2, and the top of the fraction is always a 1. Okay, so people often express that the harder direction is, given a series, come up with the formula for it, so have a couple of those. You can start the indices, instead of at 0, you could start the indices wherever works for you. 0 is fine, but somewhere else if that works. Okay, squares on the bottom, tops are always 1. The very first term is 1 over 1, not 1 over 0. So I started the indices at 1. Next one. Okay, the tops are always 7. The bottoms are the powers of 3. Next one. Okay, alternating signs. The numerators go 2, 3, 4, 5. The denominators go 1, 2, 3, 4. Okay, so we're ready. So the definition of a series, the sort of central point of the chapter, and this is the big point here of the day. So the infinite summation is called an infinite series. Its value is the limit of the sequence of partial sums. So I started with the motivation by refreshing a person's memory on this. So we're looking at A0, then A0 plus A1, then A0 plus A1 plus A2, and that forms a sequence. Those numbers form a sequence, and the limit of that sequence is, by definition, what happens with all those numbers when you add those numbers up. We're not going to do x's for the moment. At the moment, we're just going to do limit. We're going to have numbers for the AI. As with any sequence, if the limit exists, then we say that the series converges. Otherwise, we say that the series diverges. And again, I'm considering the infinite sum, just trying to have a sort of a touchstone that I come back to over and over again. So it is this series here, the x to the j in the numerator and j factorial in the denominator, and plugging in x equals 2 gives a bunch of numbers. That's a 1, that's a 3, etc. That's a number, that's a number. So plugging in x equals 2 gives a number for each case. And we ask ourselves, what is the limit of those numbers? That's a sequence of numbers. What is the limit? Likewise, plugging in x equals minus 0.5 gives 1, 2, 3. This is the sequence of partial sums. And we're asking, what is the limit of those numbers? Now, it's a discrete limit. And again, we had to talk about that last time. What's the limit of a discrete sequence? But anyway, we talked about it. In general, then, for this last one, I just went with minus 0.5, just to give an example. This is the general term. This is what a sub j looks like here in the sequence of partial sums. Okay? Okay, so that's a sequence of numbers, and we're looking for the limit of that discrete sequence of numbers. That is, by definition, what this adds to. Okay, so because it's so important, I want to do at least a little bit of practice. I know we've talked about it already in the previous videos, and we're going to talk about it plenty more as the course moves on, but it is the central point. It is the thing about which people get, if you're going to get confused, this is going to be it. So want to work with it. Okay, so I want to find the first 5 partial sums. Oops, forgive me, hit the button. First 5 partial sums, and then you want to guess the sum of the series. Now, guess is always a little flaky, but it's 1.938. I mean, what do you think the answer is? Okay, so I plugged in n equals 0, and I just got 1 over 2 to the 0. That's 1 over 1, 1. I plugged in n equals 1. You see it says 3 halves there? That comes from 1 over 1 plus 1 over 2. I plugged in n equals 2. Plugged in n equals 2 here. This right here, this partial sum, this is 1 over 1 plus 1 over 2 plus 1 over 4. And etc. And I calculated the values just to try to make it concrete, and I got 1.938. And so if I asked you to guess what are those numbers, what is the limit of this sequence of numbers, I think you would guess 2, and you would be right. Okay, next one, 4 over 3 to the n. So again, plugging in n equals 0, plugging in n equals 1, plugging in n equals 2, plugging in n equals 3, plugging in n equals 4. So just to pick on one, how about n equals 3? So 4 over 3 to the 0, 4 over 3 to the 1, 4 over 3 to the 2, 9, of course, 4 over 3 to the 3, 4 over 3 to the 4. Okay, turns out to be 160 over 27. I got my computer to do that. I didn't do that. And it comes to 5.926. And when you ask yourself, what is the limit of this sequence? I mean, I think, I don't want to put words in your mouth, but I think a person would say 6. Turns out that's right. We'll see later on in the course that that's right. Okay, so by definition, this infinite sum and this infinite sum, by definition, they are, you write down the partial sums and you take the limit of this sequence. Okay? Okay. So another example, just trying to do some examples. There's, of course, going to be homework that is like this. So the sum, starting with n equals 1, because you don't want to have n equals 0. So starting with n equals 1, the sum of the 1 over n times n plus 1s. And it's easy enough to take out a calculator or a computer and figure out the first couple of partial sums. Okay. Sorry, I had a little glitch there. So we figure out the partial sums here, and a person could try to guess what's happening here. I think if you tried to guess what's happening with the sequence of numbers, I think you would probably guess 1. And you can ask, why? How can you conclude that instead of just guessing? And the answer is, you can figure out from partial fractions, or however, just splitting it by I, or whatever you do, that 1 over n times n plus 1 is 1 over n minus 1 over n plus 1. And again, the partial fractions would do that, or sometimes you can just get it by I. There's something to notice here when you have a sub n is 1 over n minus 1 over n plus 1, and I think it's easiest to notice it with an example, so I did the partial sum S5. So here is the 0th term, here is the 1th, the 1th term, this is the 2th term, the 3rd term, the 4th term, and the 5th term. And do you notice that the minus 1/2 cancels with the plus 1/2, and the minus 1/3 cancels with the plus 1/3, and of course all the others? So what you end with is a 1 over 1 and a 1 over 6 with a minus sign between them. Where the thing was long and then it gets short is called telescoping, where a series does that. It's like an old pirate telescope. You know how you start with a long telescope and you clap it close. So the sum telescope shrinking from long to short, and so what you end up with for S sub n is 1 minus 1 over n plus 1, and so obviously when n goes to infinity, that goes to 1. Okay, so again, the major point of this slide is not so much the partial fractions stuff as it is that we are finding what is the capital S sub 1, capital S sub 2, capital S sub 3 in a way that is not numerical. We were able to find it algebraically. And it turns out to then be possible to take the limit of the capital S sub n's in an algebraic way and get an answer. Okay. The previous slide we've talked about some things, and just want to make sure that because people so often get lost in this chapter, will confess to feeling a little lost in this chapter, I want to make sure that we keep repeating the couple of points over and over again so that a person can keep them in their mind. So often for us with a series, the challenge will not be finding the formula for the series. Instead, for the series that we look at, the challenge will be whether the series converges. That is to say, whether the sequence of partial sums has a limit. So there's plenty of things that a person could work on with series, and a person could spend their life working on different series. But for us in this class, the challenge will usually be figuring out whether a series converges. That it will converge for some numbers when you plug those numbers in for x, it'll converge for some numbers, and will fail to converge for others. That will happen sometimes, and the difficulty for us will be figuring out when it converges. So, for instance, we won't have much trouble coming up with the prototype infinite sum that we have as the expansion of e to the x. The trouble that we will have will be establishing that when an infinite sum equals that function, specifically for which x's the sum converges. Okay. Okay. So, time to start some examples. And the first example is certainly going to be the most important infinite series, the geometric series. So a geometric series is the sum of a geometric sequence. So you see in these two capital S's, you see that we're looking at AR squared, AR cubed, AR to the fourth. So to go from term to term in this series, you multiply by R. So common ratio, you multiply by R. Now, you can have a finite geometric series or you can have an infinite geometric series, and we're going to do both. The infinite one is the one that we are typically going to be doing on the homework. But I have a comment about the finite geometric series. So I'm not sure what I mean by this, but I'm going to say it anyway. When you're a professional mathematician and you have a large family, people in your family will tell their kids, ask your Uncle Jim about that. So I get emails from nephews, nieces, cousins, kind of stuff, asking about some math question that arose. I don't get hundreds, but from time to time I get questions. Sort of 9 times out of 10, or 8 times out of 10, but a lot. The question is answered by a finite geometric series. It just is something that comes up a lot. And we'll see a couple of examples. I'm going to do a couple of examples in a few minutes. But it is just something that occurs a lot in kind of everyday life. Okay, so just as a side comment. All right, so there I have a finite geometric series. And the theorem claims that this is the sum. Except in the r equals 1 case. Anyway, this is the sum. Okay, so how do you prove that? And the answer is you write down the formula for capital S sub n, multiply by r to get r times capital S sub n. Okay? So you have a plus ar squared plus all the way up to plus ar to the n plus 1. No, ar to the n. Forgive me. I was trying to think and write at the same time. That's a mistake. Okay, and that's equal to capital S sub n. And you multiply by r times capital S sub n. So that gives you ar plus ar squared plus all the way out to plus ar n plus 1. Because look, when you multiply this by r, for example, you get ar n plus 1. When you multiply this by r, you get ar. So you get what I said you get. Please subtract. Okay, this a doesn't have anybody to cancel with, so you just get a. There's cancel. There's cancel. All the way out to there's cancel, and you're left with a minus ar to the n plus 1. Okay, factor out an r. Factor out an a. A times 1 minus r to the n plus 1. That's what happens on the right. On the left, you're looking at 1 minus r times s sub n. Lost my parenthesis. Divide both sides by 1 minus r and you're done. Obviously, you have to worry about what happens when r equals 1, but anyway, you're done. So just as a corollary, there are two examples of a finite geometric series that come up a lot, but I already commented that it just seems like finite geometric series is one of those formulas that a person should know. That if you're claiming to know some things about math, this is one of the things you should be walking around with. Anyway, 1 plus 2 plus 3 plus 4, etc. So if you take 1 plus 2 plus 4 plus 8, I said 3, I misspoke. So 1 plus 2 plus 4 plus 8, let's see, 2 plus 8 makes 10, 4 plus 1 makes 5, so we're looking at 15. And the theorem says that that is not 8, but instead 16 minus 1. So you go to the last number here and take the next higher power of 2 and subtract 1. Okay, so not 8, but 16. Take away 1. And then what happens here if instead of having a common factor of 2, if you have a common factor of 1/2, 1/2 plus 1/4 all the way out to plus 1 over 2 to the n adds to 1 minus 1 over 2 to the n, and probably the two formulas remind you of each other. Well, the first one's very straightforward from the formula that's up here. The first one's very straightforward. Put a equals 1 and r equals 2, just gives you the straightaway formula. Okay, for the second, this is maybe not the first thing you would think to do, but it proves to be easier with the ends. So you take a equals 1 and r equals 1/2. If you take a equals 1 and r equals 1/2, etc., then you get this expression here. That gives you this formula straight from star. That's just the formula, and that's this. But now I have, compared to what I want, I have a 1 that that's surplus. So subtract 1 from both sides, and you get the formula. You get the formula that one. Okay, so a person should know all three formulas. A person who knows mathematics should know all three formulas here. This one here, this one, and these two. Okay, just walking around should know those formulas. For the infinite geometric series, you're going to look at the sequence of partial sums. So we calculated the s sub n's on the prior slide, and now I'm going to take the limit. Okay, let's see. So for the infinite sum, I've got to look at the limit of the sequence of partial sums. That's exactly what it says, the limit of the sequence of partial sums. And I gave the formula for the partial sums on the prior slide. Okay, so what happens is that this is s of n. Okay, from the prior slide. Okay, we take the limit here as take the limit here as n goes to infinity and ask what happens to different r's. Well, if r is less than 1, let's say r is 1/3. If r is less than 1, then the limit of, if r is less than 1, then the limit of the expression on the right is positive 1. If r is 1/3 and you take the increasingly high powers of 1/3, you're looking at 1 minus 0. So you get a over 1 minus r, and that's what it says. So if the absolute value of r is less than 1, then you're getting what it says. If the absolute value of r is greater than 1, so suppose that r is 15, then you're looking at 1 minus the powers of 15, and so you're looking at numbers that are going to infinity. All right, what about if r equals 1? So in the case where the absolute value of r is 1, you're looking at plus 1 or minus 1. Here's the plus 1 sum, here's the minus 1 sum. In both cases, you get divergence. In the first case, because it goes to infinity. In the second place, because it alternates sign. Except in the, this is kind of a dopey case, the a is equal to 0 case. Okay, so that gives us this formula. So we can add up infinitely many numbers in the case where the sum has this form, where there's a common ratio. All right, we need for the absolute value of r to be less than 1, but nonetheless we can add up infinitely many numbers. Okay, so just as an example, here are two examples on the slide. The first has a common ratio of minus 1/2, and if you look at the sequence of partial sums, the first partial sum is 3, the second partial sum is 1.5, 2.25, 1.875, 2.062, etc. here. So when the ratio is minus 1/2, we're looking at numbers that are kind of ping-ponging back and forth, but nonetheless zeroing in on a total of 2. If the common ratio is minus 5/2, then here are the partial sums. We're looking at numbers that are ping-ponging back and forth, again, plus, minus, but they are clearly getting bigger. They're not zeroing in on something, they're getting bigger. Okay, so a form is a formula, and a person can plug in and absolutely get what's happening, but nonetheless, the point is that we are looking at the sequence of partial sums. That's the major point for the day, is that the way we add up infinitely many numbers is we look at the sequence of partial sums. A formula is great. You need the formula for the homework. You should memorize the formula. Go for it. But I don't want it to get away from a person that we're looking at the sequence of partial sums. So I have a couple of applications. I'm trying to emphasize that the material that we're doing is intellectually interesting, has many applications, as well as being just sort of things that a person tries to get through on the homework. So the celebrated Greek philosopher Zeno proposed a paradox. He's trying to talk about the difficulty of reasoning in a certain way, but we're not interested in going into it. We're simply going to talk about the paradox. So Zeno asserts, consider the following argument. I'm going to argue that motion is impossible. Okay, now of course it doesn't really mean motion is impossible, but we're going to consider the argument without the background. So suppose that the hero Atalanta wishes to walk to the end of a path. First, she has to pass through the point halfway to the end of the path. Then she has to pass through the point 3/4 of the way to the end of the path. Then she has to pass through the point 7/8 of the way to the end of the point. Thus, to walk to the end of the path, she has to complete an infinite number of tasks in a finite time. You can't complete an infinite number of tasks in a finite time. That's obviously impossible, Zeno asserts. Mathematicians resolve that paradox by saying, well, let's look at this infinite geometric series, which we happened to look at a few minutes ago, 1/2 plus 1/4 plus 1/8. So suppose it happens to be the case with the path and her pace that she passes through the halfway point in a half a minute. And then it takes her to get from the halfway point to the 3/4 way point, it takes her, perhaps not surprisingly, a quarter of a minute. And then to go the extra eighth, the next eighth, she takes her an eighth of a minute, and then etc. Then you find yourself saying the total time taken is this. And we know that adds to 1. So she, she doesn't have any trouble accomplishing an infinite number of tasks in a finite time. Okay, so it's a rejoinder to Zeno's dichotomy paradox. Another application. I want to talk about the difference between 0.9999999, etc., and 1.00000. When people first see this question, they often say something like, well, numbers that look different are different. I mean, 50 and 51 look different. They have different representations, so they're different numbers. But that person is mistaken. Okay, each digit in a decimal representation is associated with a power of 10. So 0.99999, it can be thought of as a shorthand way of writing. Take the 0.9 and then the 0.09 and then the 0.009 and etc. and add them all up. So here's the 0.9, here's the 0.09, here's the 0.009, and add them all up. That's a geometric series. So the 0.9, the 0.09, and the 0.009, and add them all up. It's a geometric series. I happen to factor a 9/10 out of every term, and that left me with the first term was 1, the second term is 1/10, the third term is 1/100th, etc. Formula for the geometric series gives 1 over 1 minus 1/10, 1 over 1 minus r. And when you take 1 minus 1/10, you have 9/10, and because it's on the bottom of fraction, you invert and multiply, it becomes 10/9. Do the cancellation. Do the cancellation, you're looking at 1. So 0.9999999 is the number 1, has a value of 1. So just as a comment here, this multiple representation where a single number can have 2 ways of writing it only happens in a decimal system for numbers where one of them ends in 99999 and the other ends in 00000. Okay, and I gave you a reference that you could look at. Okay, another comment, another application of geometric series. This happens to be a finite geometric series, but anyway, still a geometric series. So suppose you have an investment that pays $10,000 per year, maybe rental property. Anyway, you have an investment that pays you $10,000 per year. I'll take the inflation rate to be 5%, just for a number. And so I have to discount future earnings at that rate. The $10,000 that I get a year from now is equivalent to how much money today? Well, if I took $9,523 and 81 cents at today and put it in the bank at 5% interest, then in a year I'd have $10,000. So that means that $10,000 a year from now is equivalent to 95.2381 today. Okay, so if I ask then how much is the money this year plus next year plus the year after plus the year after, how much is that worth in total? I get an infinite stream of income. I get an infinite stream of income that is a geometric series. The common ratio is going to be 1 over 1.05. I factored out a 10,000 just to make the numbers easier. Anyway, I factored out 10,000. It fits the formula. There we go. We get A times 1 over 1 minus R. And when you invert and multiply, cancel, you get $210,000. So getting $10,000 a year in a climate where the inflation rate is 5%, getting $10,000 a year is the equivalent of being paid $210,000 today. Said another way, if you had $210,000 today and you put it in the bank, you could take out, I put it in the bank at 5%, you could take out $10,000 per year, and by the time you came back there next year, the interest rate would have brought it up to $210,000 again. Okay, so you get an infinite stream of income. And now here I mentioned a finite geometric series. This example is going to use a finite geometric series. So suppose you buy a house with a $400,000 30-year mortgage, traditional 30-year mortgage, and the annual rate is 7%. You know, I Googled around and it said 7% when I looked the other day. Paid monthly, you often pay a mortgage monthly. How much do you pay per month? So the $400,000, and we're asking $400,000 is a present value of this stream of income. Now this stream of income only lasts 360 months, doesn't last forever. But anyway, $400,000 is the present value of this stream of income, of this stream of payments. Okay, I plugged it into, I mean the numbers are ugly, but I plugged it into the formula for a finite geometric series. Factored this out of each term, and what I was left with here, 1 minus r to the n plus 1, so 360 it says, because I factored one of them out in order to make this term, and then you add n plus 1, so you back up to 360, and so you're looking at this. And when you do the calculation, again, the number's a little ugly, but when you do the calculation, the per month is $2,661.21. Okay, so again, just trying to give some sense that these series come up a lot. I don't know, when I get an email from a nephew or something, 9 times out of 10, it has to do with geometric series. Okay, I mentioned before that, that this is a long series of videos, and it might be a good idea to pause it, go get a drink of water. This is a good spot. This is about the halfway spot. Okay, it's a long series of slides. This is about the halfway spot. Okay, we've defined series, and I want to talk about when the series converge. So, this is the important result. If you have two series that are convergent, then so is the series of linear combinations. So if, for example, you want to take 3an plus 5bn, that series will also converge, and it'll add to the obvious thing, 3 times the sum of the first series plus 5 times the sum of the second. Some special cases are that you can bring out a constant. There, the B series is all zeros. Here, if you take C and D to be 1, then you get the conclusion that you can break a series, break a summation along a plus sign. And if you take a C to be 1 and D to be minus 1, then you get the conclusion that you can break a series along a minus sign. Okay, so here's a typical example here. So I want to find the sum of this infinite series. I'll split the fraction along the minus sign. There we go. 2 to the n plus 1 over 5 to the n, and 1 over 5 to the n. And I'm looking at 2 to the n plus 1 over 5 to the n series, 1 over 5 to the n series. So in between, I broke along the minus sign. I got 2 series. 2 to the n plus 1 over 5 to the n is not quite the form I need. I need 2 to the n over 5 to the n, and so I factored out a 2. And what was left then was 2 over 5 to the n. Well, the other series was already in the form that I can get into 1 over 5 to the n, and now just plug into the 1 over 1 minus r, 1 over 1 minus r, and do the arithmetic. Okay. So the algebra of convergent series is that you can do sums in this way. I'm only going to briefly go through the argument. As usual in this course, we emphasize the arguments less than using them. But the whole point of the argument is that you get the partial sums of the A's and the partial sums of the B's, and you work with the partial sums. So the point of an infinite series is that it is by definition the limit of the partial sums. So when I want to talk about what is happening to CAN plus DBN, that series, I want to look at the limit of its partial sums. I want to look at the limit of its partial sums. So there is this whole thing right here is S sub capital N. Okay? So I break that thing along the plus sign, I factor out a C and a D, and so then I'm looking at the limit of the partial sums of the A's and the limit of the partial sum of the B's, and that's what it said in the original result. Those are convergent. Okay. So a couple of examples here. So for example, I have a series that has a plus sign in the numerator, so I broke it into two series where one of them is 5/7 to the n and the other is 3/7 to the n. 1 over 1 minus r, 1 over 1 minus r, and it adds up to some number. Another example, just a somewhat more complicated example, but not all that much more complicated example. So here, thinking to do much the same thing, I'm thinking to bring out a 5. That leaves me with 3 to the n over 4 to the n plus 2. Not quite what I need. It's not quite 3 over 4. So I brought out a 4 to the 2. There it is. Brought out a 4 to the 2. That left me with 4 to the n on the bottom. And now I have 3/4 to the n. 1 over 1 minus r, and you get an answer. Okay, so I turned, in each case, I turned them into the suitable for the formula for a geometric series. Okay, one of the lessons that we'll see as a consequence of the definition of the sum of an infinite series is that whether the series converges doesn't depend on the initial bunch of numbers. If the first number is a 92 and the second number is a 34 and the third number is a minus 17, none of that matters. What matters is what happens to the numbers in the tail. Say the number's bigger than 100, or the number's bigger than 1,000, or the a sub n's where n is bigger than 1,000,000. And that's what the lemma says. The lemma says, pick a capital M, say 1,000,000. Then the series of all the terms converges if and only if the series of terms numbered bigger than 1,000,000 converges. That is to say, convergence depends on the tail. And the proof, I'm not going to actually go through the proof. The point is that you again look at the sequence of partial sums. You look at the sequence of partial sums. Okay, so convergence of a series depends only on its tail entries, that is to say the partial sums for large indices. Okay, now, so we talked about convergent for a little bit, talked about geometric series. Now we're going to talk a little bit about divergent series. And the lesson with divergent series is that divergent series, you can't do the kind of arithmetic you can do with convergent. So whenever the arithmetic goes wrong, it's because you're using a divergent series somewhere. So just as an example, clearly this series is divergent because its partial sums go 1, then 0, then 1, then 0. I mean, you know, you just don't get here. You just don't get a pattern in the sequence of partial sums. Okay, and for the same reason, the series that alternates only opposite, it doesn't start with +1, it starts with -1, alternates with starting with -1 is also divergent. But if you add them together, then you will get, if you add them, then you'll get a first term that is 1 minus 1, and a second term, a second partial sum that is a second partial sum that likewise gives you 0. A third partial sum that likewise, my pen, it likewise gives you 0, and etc. So you take two divergent series and you appear to be able to add them to get a convergent series. But it's easy to think of two divergent series where you add them and it still diverges. Take S twice, add it to itself. So divergent series can't be trusted. You can't do the arithmetic on divergent series that you do on convergent series. Okay, the harmonic series. This series is in the section that I've called divergent series. So guess what? It diverges. I'll just make a 10-second comment on the word harmonic. It has to do with when you're playing like a string instrument, where it is where do you get harmony? I'm not going to go into it, but the harmonic is not an accident. And it is 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. I've done some examples where this series came up earlier. It is a very important series. So, if we're going to list sort of the 10 most important, this certainly is one of them. And the harmonic series diverges. In order to show it diverges, I'm going to show that when you look at its partial sums, 1, comma, 1 plus a half, comma, 1 plus a half plus a third, comma, etc. When you look at those partial sums, those numbers make a sequence of numbers that goes to infinity. All right, so what to do? Here are the partial sums: 1, 1 plus a half, 1 plus a half plus a third, etc. That's a sequence of numbers, infinitely many sequence of numbers. I'm going to show that sequence has a limit of infinity. Okay, so it's a little tricky, but not awfully tricky. So you look at S sub 1. There it is, right there, 1. Then you look at S sub 2. There it is, right there, 1.5. And then you skip S sub 3 and instead look at S sub 4. 1 plus a half plus a third plus a quarter. So 1 plus a half, I'm going to ignore that. The third plus a quarter, both 1/3 and 1/4 are bigger than or equal to a quarter. So 1/3 is bigger than a quarter. I'd rather have a third of a pie than a quarter of a pie. So this here is bigger than 2 times a quarter. So I have 1 plus a half, which adds to 1.5, and here's another half. So S4 is bigger than or equal to, but it's bigger than 2. So S1 is bigger than or equal to 1, S2 is bigger than or equal to 1.5, S4 is bigger than or equal to 2, S8, the exact same trick, bigger than or equal to 2.5. So if you pay attention to those partial sums, there's nothing wrong with the other partial sums, but just simply focus your attention on the partial sums that have a power of 2 in the subscript. You're looking at numbers 1, 1.5, 2, 2.5, 3, 3.5. I mean, they're going to infinity. So the sequence of partial sums diverges to infinity. So that means that the infinite series given here adds to infinity. Okay, by definition of what it means to have that infinite series. Okay. So we're going to go through and talk about divergence, and the most important fact about divergence is that if a series of terms converges, then necessarily its terms have to go to 0. Then necessarily the individual a sub n's have to go to 0. So if you are to add up a bunch of numbers and have them go to 0, then it must be the case that the individual numbers go to 0. If we add numbers that don't go to 0, 1 plus 2 plus 3 plus 4, I mean, there's no way that adds to anything less than infinity, right? So if the individual numbers, 2, 3, 4, have a limit of infinity, I mean, you have no hope of adding to something less than infinity. If you want to add numbers that have in total a finite value, so I'll take the geometric series here, you got to have it be the case that the individual numbers, the 1, the 1/10, the 1/100th, are going to 0. Okay, and that's exactly what the lemma says. It says that if the sum is to be finite, then the individual terms have to go to 0. Terms, okay, not the total, terms. And again, we don't typically do the proofs, but I think that writing down some numbers makes it clear. Okay, and we typically use the divergence test. It talks about converges, but we call it the divergence test because we typically use it to show that a series has to diverge by showing that its terms don't go to 0. So when the lemma says if a series converges, then its terms go to 0, we're going to typically use it in the form that if the terms do not go to 0, then the series does not converge. So here's an example of a series. I'm going to show that the terms do not have a limit of 0. So I'll show that the limit of the sequence 3n squared plus 2n over 4n squared minus 1, where the n's are bigger than or equal to 0, that sequence does not have a limit of 0. And I'll show that in the way that we've been typically showing things about discrete limits, is that I'll convert to the associated real number function, 3x squared plus 2x, 4x squared minus 1, and that limit is infinity. That limit is 3/4. Sorry, had a brain cramp. You can find the limit in a number of ways, but I'll just say L'Hopital's rule. Okay, and just comment, the converse of the divergence test does not hold. So the divergence test says that if the series converges, then the terms go to 0. The converse would be that if the terms go to 0, then the series converges. That's not right. So if the terms go to 0, that does not necessarily imply that the series converges. And the harmonic series is an example. Its terms 1, 1/2, 1/3, 1/4 go to 0, but the series as a whole does not converge. Okay. So the divergence test is typically used to show that a series diverges. Practice, please. And again, I urge you to pause the video, try it, come back. So I'll give you a second to pause the video. Okay, great. So when you take the limit of the sequence, not the limit of the sums, forgive me, but what folks ever get wrong about this is they start worrying about the partial sums. So take the limit of the sequence, n cubed over 3 plus n cubed. My pen, my handwriting really. N cubed 3 over n plus n cubed, where the n's are bigger than or equal to 1. I don't know. I took the n's bigger than, I could have taken the n's bigger than or equal to 0. I took 1 just to practice with other numbers. That's all. Anyway, those terms don't go to 0. They go to 1. If n is 100 billion, then the 3 on the bottom doesn't make any difference. You're looking at n cubed over n cubed, and so you're looking at 1. Okay, next one, please. Okay, great. The sequence of terms does not have any limit at all, since they ping pong back and forth between about 1 and about minus 1, because on account of the powers of minus 1. Okay, so I'm not paying attention to the sum. I'm paying attention only to the terms. Easy to get confused here. The sum does not. The numbers do not add to a fixed sum. The infinite sum diverges because the sequence of terms diverges. I absolutely concede that that is difficult. That's why I've been warning all along with all these videos that this is a chapter where folks find themselves getting confused. It's very easy to do. Okay, good. So emphasize throughout the day that this is about the difference between a series and a sequence, is that a series is defined to add to the limit of the sequence of partial sums. And I absolutely agree that a person can get confused. That's why we have homework, and that's why I have practice. But to sort of as a payoff for working with a very difficult topic, I'm sorry, I think it's difficult. I don't want to keep banging on it, but I think it is. I want to acknowledge that it's difficult. Okay, so I want to do something for fun. So imagine that we have a set of blocks. So I think of them as dominoes, and a set of blocks, and they have the property of being two wide, and one long. Okay, so they are each of them 2 wide, and each of them has a mass of 1. I could have made the mass be 0.07, but it just make it hard. So I made the mass of 1. But it matters that they're 2 long. Okay, I can pick one of the 2 blocks and put it on top of the other so that it sticks out a little bit. There, it's sticking out a little bit. All right. The top block won't fall so long as it overhangs by 1 or less. So if this is 1 or less. Okay. Now I want to think of that as a 2-block system, so that you might imagine gluing those 2 together, sort of a light brown and a somewhat darker brown, gluing those 2 together. Then what you get is a single system. What's its center of mass? Okay, let's see. So there's a one block whose center of mass is at x equals 1. There's a block whose center of mass is at x equals 1. And there's another block whose center of mass is, sorry, I misspoke. This is the block on top as a center of mass above 2. And there's another block whose center of mass is above 1. So weighs 1, center of mass at 2. Weighs 1, center of mass at 1. I know its mass is 1, but I'm being a little loose. So in total, the two-block system, if you imagine gluing these two together, the two-block system would have a center of mass at 3/2. So if you took your finger and whoops, did I get version 6? I can say it was drawn by AI. If you took your finger and you could balance it left versus right by putting your finger at the 3/2 point. Okay? Okay. That means that I could take that two-block system and push it out on the edge of the table until it overhangs, push the two-block system out until it overhangs by a half, namely this half. Okay? When you do that, you haven't, this distance is an overhang of 1, this distance is an overhang of a half. Okay? That system won't fall because that's the center of mass here. You imagine with your finger that you've got it balanced there. All right, you can see what I'm going to do. I'm going to put a new block in. The way that I put a new block in, though, is I don't put it on top. Instead, I pick up the two blocks, and I stick a new one underneath it. Underneath it, on the bottom. Okay, so pick up the two blocks and stick a new one underneath it. So the top block here is hanging out into empty space by a total of 3/4. Can you put new blocks underneath to make the top one stick out even further? What's the maximum possible stick out? So the prior slide says that the two-block system has a center of mass above 3/2. So we can put it on the top of the third block, hang out until it overhangs by 1/2. So the two-block system is overhanging by 1/2. What's the center of mass of now the three-block system? Okay, well, let's see. I have a mass of 2 centered at location 2. I have a mass of 1 centered at location 1. Well, a mass of 2, that's the top system, centered at location 2, at x equals 2. A mass of 1, the bottom block, the new block that I've just shoved in, centered at location 1, and the total mass is 3. So the center of mass of this three-block system, there is the center of mass of this three-block system. Oh, I'm going to draw in my little thing with the finger. So the center of mass of this three-block system is 5/2. If you put your finger at 5/2, it would balance left and right. Okay, so that means you can put it down on the table and push it out until it did I say 5/2? 5/3. If you 1/3, if you put it on the edge of the table, you can push it out until there's that 1/3. And now the top block here sticks out by 1 plus 1/2 plus 1/3. When you add those up, they add to 11/6, not quite 12/6, so not quite the entire length 2 of the top block, not quite the entire length 2, but a lot of it, nearly entirely in free space. So, worked once, let's try it again. We'll consider this a three-block system. We'll lift it up, and we'll stick a new block underneath. So we get a 4-block system. You get the idea. We get a 4-block system where the overhang is 1/3. And this, of course, is an overhang. Oh, that's the 3. Overhang of a half and overhang of 1. So this is the 3-block system right here. And we stuck a new block underneath. What's the center of mass of this 4-block system? Well, this 3-block system here has a mass of 3 and a center of mass located above the point x equals 2. This has a mass of 1 and it's located above the point x equals 1. So a mass of 3 located above x equals 2, a mass of 1 located above x equals 1, and the total mass for the entire is 4. You're looking at 7/4. And so that means there is too much scribbling on the page. That means there is a 1/4 down there. And of course, you're looking at a 1, a 1/2, a 1/3, a 1/4. You get the idea, of course you do. And this top block is sticking out entirely into free space. The top block, it's crazy, sticks out entirely into free space. The top block, of course, is too long, so that would be 24/12. But it in fact sticks all the way out to our right. This is above, right here, this is above x equals 25/12. So the entire block, 25/12 it says, the entire block is in free space. I mean, when will the madness end? when does it stop? So of course it doesn't ever stop. So in general, you take the n block system. I just took a 4 block system. I took a 3 block system. You took a 3 block system, and I stuck in a 4th block to make a 4 block system. So in general, you take an n block system and you put it on top of an n plus 1th block, and you overhang it by 1/n. The center of mass of the new system is the n block system. The n block system is now located above x equals 2. The 1 block, new block, is located above x equals 1, and there's a total mass of n plus 1, and you get this. Okay, so clearly the amount by which the top block sticks out is unbounded. The amount by which the top block sticks out is unbounded. Okay, isn't that nice? Very nice. Okay, very good. So a long video, a lot to get down, but for the rest of the chapter, the points that we made are important to get down. In particular, that the sum of an infinite series is defined to be the limit of the sequence of partial sums. Okay, very good.